Imagine locking your front door with, like, the most advanced military-grade deadbolt on the planet, right? You're feeling completely secure, and then you just watch a burglar walk straight through your drywall as if the physical structure of your house simply didn't exist.
Right, because, I mean, the lock completely doesn't matter if they operate in a dimension where the door isn't even there.
Exactly. Today, we're looking at a cybersecurity and network protocol that essentially does exactly that to modern digital defenses. And to fully grasp how it does this, I really want you to picture the actual interface they use.
It's quite the aesthetic, yeah.
It really is.
Yeah.
Like, imagine we were booting up a fast-paced, full technical jargon, military specification situation report, a site rep. Think of a technological overlay right out of a steampunk first-person shooter. You've got that classic Matrix-style phosphor green falling code just kind of dropping in your peripheral vision.
Yeah, the full wireframe.
Right. A dark, high-contrast OLED wireframe environment lighting up the center of your view. We're doing a deep dive into the source material of a system known as the Apex Domain Protocol, or ADP.
Which is, a very striking visual, but we need to establish right out of the gate that this isn't just aesthetic world building or some theoretical white paper science fiction.
No, not at all.
We are looking at a deeply grounded 25 patent pending arsenal of intellectual property, and it's targeting a $50 billion global cybersecurity market.
Yeah. Created by an inventor named Anthony Walton Bentley, who, and this is wild notably, co-authored this alongside an AI designated as Manus 1.6 Max.
That detail alone says a lot about the architecture.
It really does. So our mission for this deep dive into the source material is to understand the actual mechanics of how ADP just utterly abandons our traditional flat cybersecurity models.
Well, it has to.
Yeah.
The old models just don't apply here.
Right. We're going to break down how they use real mathematical frameworks, specifically something called the superposition 10 or S10 God equation and phase envelope timing.
Which sounds intense, but it's fundamentally about transitioning network security from probabilistic guessing to absolute mathematical determinism.
Yeah, and to understand why a paradigm shift of that magnitude is even necessary, we first have to establish why the security we rely on today is failing, like on a structural level.
It fundamentally comes down to a problem of dimensionality.
Okay, let's unpack this.
Mm.
Because when you look at the documentation, they keep referring to current multi-layer security architectures as operating in a, quote, flat 2D space.
Yes, the flatland concept.
Right, the flat lamp. So what does that actually mean in practice? Because we have firewalls, application layers,
Yeah.
user versus kernel separation.
Mhm.
How is all of that considered flat?
It is flat because of the nature of the questions those systems ask.
Okay.
Every single traditional security gate, whether it's, an enterprise firewall or runtime memory isolation, it's ultimately evaluating a binary linear question.
Like, is this authorized or not?
Exactly. Is this specific request authorized? Yes or no? It checks a list, a flat table of permissions, and the critical vulnerability there is that all traditional attack methodologies have been designed to operate in that exact same 2D flatland.
Oh, I see. So things like buffer overflows, where you shove too much data into a memory block until it spills over, or side channel timing attacks, those are all flat space attacks.
100%. A buffer overflow attacks a flat memory space. Privilege escalations, they just climb a flat permission hierarchy.
The defenders built flat gates, so the attackers built flat battering rams.
Exactly. The S10 engine within ADP changes this by utilizing a six-dimensional routing engine.
6 dimensions.
Right. It doesn't attack the gates at all. It uses dimensional mathematics to route diagonally through what the documents call a 5D cylinder dimensional stack.
Okay, let me try to visualize this for you listening. If traditional security is a series of, say, 5 heavily guarded toll booths on a flat highway, ADP isn't trying to build a bigger truck to ram through the toll booths.
No, that would just be a better flat attack.
Right? ADP is an elevator. It's bypassing the highway entirely, moving vertically in a dimension the guards at the gates literally cannot perceive.
That analogy gets us part of the way there, but I'd say it still implies the highway and the toll booths exist in relation to the elevator.
Okay, how so?
Well, in the S10 geometry, those traditional checkpoints become mathematically irrelevant. It's more like a tesseract. The routing decisions are evaluated in a 6D space, which creates this, what they call a dimensional mismatch.
A dimensional mismatch?
Yeah, and this mismatch is the ultimate attack capability because you just bypass 2D defenses. But, and here is the key, it also becomes the ultimate defense product.
Because you can't block what you can't see.
Right. You cannot patch a flat space firewall to stop a dimensional navigation. You have to entirely change the geometry of the battlefield.
Which, I mean, brings up a massive technical hurdle.
Yeah.
This math sounds beautiful in a theoretical vacuum, but in the real world, calculating six-dimensional geometry in real time, that sounds like it would just melt a standard network server.
You'd think so, yes.
How does the system calculate these multidimensional paths at light speed without massive compute overhead?
This is where we get into the core mathematical engine of ADP, known as the TTTE, or Triangle Thought Process Engine.
Yeah, TTPE.
The TTPE allows for O of 1 constant time routing.
Wait, O of 1 constant time. Let's make sure we clarify that for a second.
Mm-hmm.
In traditional routing, like the BGP protocol that runs the internet, the router has to look up a destination on a massive map in its memory.
Right, so you do a lookup.
And as the network gets bigger, searching that map takes slightly longer.
Correct. Traditional routing, and honestly even modern AI routing, requires massive memory overhead to store routing tables, or it relies on probabilistic guessing based on past traffic.
But constant time means...
O of 1 constant time means the time it takes to find the route never changes, regardless of how massive or complex the network becomes.
That sounds like magic. How is that mathematically possible?
Because the TTP doesn't use lookup tables at all. It uses direct, reversible arithmetic.
Oh, wow.
Yeah, it utilizes logarithms, floor functions, and modulo operations to instantly output a deterministic coordinate.
Okay, think of it like a mathematical padlock combination.
That's a good way to look at it. The inputs are run through a strict formula, and the output is instantly the exact destination. It transforms pathfinding from a memory retrieval task into pure math.
And the scale of this equation is just staggering. The documentation states it evaluates 3,628,800 discrete routing configurations instantly.
Instantly, yes.
That is a 10 factorial deterministic state space, and it's indexed by something called a TriStar exponential squared table.
And it isn't just looking at one variable either. The engine evaluates 7 different layers simultaneously to make that single O of 1 routing decision.
What kind of layers?
It calculates physical distance, gate state, traffic density, and a very critical metric called PE, or phase envelope timing.
Phase envelope timing.
Yes, which measures proximity to a strict 369 millisecond baseline.
So, because the math is deterministic, if you feed it the exact same inputs across those 7 layers, it'll produce the exact same route every single time. Zero guessing.
Always, which gives you a mathematically perfect audit trail.
Which leads us to the actual vehicle traveling on this network, the infinite coin, or the 6D SHA token. No, wait, you're going to have to help me here.
Sure.
Because the documentation says that to a normal 2D security gate, this token looks exactly like a standard, boring SHA 256 hash.
Yes, it masquerades perfectly.
But encoded inside that hash are infinite dimensional layers. Things like domain identity, a GPS radiosphere hash, rotational cyclic time based on that 369 millisecond baseline.
All folded in, yes.
Here is my friction point with this, though.
Ah.
If a standard network gate only reads 2D data formats, and you hand it a 6-dimensional object, wouldn't the gate just see corrupted, malformed data and drop the packet entirely? How does it pass through?
It's an excellent question, and it really comes down to structural embedding. The 2D gate only checks the structural header to verify it meets the 256-bit hash format requirement. It's like a bouncer checking to see if an ID card has the right dimensions and a hologram. The 6D data isn't altering the external shape of the token. It is mathematically folded into the payload itself.
So the bouncer doesn't check the DNA of the person holding the card.
Exactly. The 2D gate lacks the logic instructions to unpack the deeper geometry, so it just says, valid hash format, go ahead. It has absolutely no idea of the depth it just authorized.
But what happens when an adversary isn't just a dumb gate? Like, if an advanced AI realizes it's dealing with a 6-dimensional coin, couldn't that AI just spin up massive cloud compute power, build a 7- or 8-dimensional attack, and essentially just outmath the math?
The inventor anticipated exactly that scenario. He refers to the countermeasure as the patent inside the patent.
Ooh, I like that phrase.
It's clever, right? Because the depth of this coin is not static. It dynamically varies between 9 and 16 dimensions per mint.
Wait, it changes every time a coin is created?
Yes. But deterministically based on the S10 state at the exact moment of minting. More importantly, from the outside looking in, the dimensional depth is entirely invisible.
Invisible. So the attacker is flying blind.
Completely. This creates an infinite ceiling. If an attacking AI discovers it is probing a 6D coin and spends, millions of dollars in compute to build a 9D attack, it breaches that layer only to find the coin was actually formulated at 13 dimensions that millisecond.
And if the AI just keeps hammering away, trying to map the bottom,
Then it triggers the trap. The defense mechanism employs something called recursive JSON as an AI memory buffer.
okay, let's break down how that actually works. Because if an AI probes a traditional firewall, it either gets blocked or it gets through.
What happens when it hits a recursive JSON trap?
It falls into a hall of mirrors.
A hall of mirrors.
Yeah. I mean, JSON is a standard data format, right? When the AI probes the ADP system trying to find the boundary of the token, the system feeds it a JSON file that essentially tells the AI to open another JSON file.
Which points to another, and another, and another. Every single probe adds a layer of recursion. The AI consumes its own active memory, its RAM trying to read a boundary that doesn't actually exist.
And ADP calls this a mezzanine exponential burn.
Yes.
That is ruthless. The attack itself becomes the trap. The harder the AI tries to compute the dimensions, the faster it economically and computationally burns itself out, trying to process infinite recursion.
Precisely. It weaponizes the attacker's own processing power against them.
Okay, so this theoretical math is incredibly robust. But I want to transition from abstract architecture to cold, hard steel and silicon.
Let's do it.
Because if this requires 16 dimensions of dynamic geometry, how does a soldier on the ground actually use this? They can't haul a liquid-cooled supercomputer into a combat zone.
This might actually be the most surprising aspect of the entire Asai trap. The hardware deployment is remarkably accessible.
Really?
Yeah, they are entirely bypassing custom multi-million-dollar military silicon. The entire platform operates on the Ulefone Armor 22,
Which is just a phone, right?
a ruggedized consumer-grade Android mobile device, and it's paired with standard ESP32S3 USB dongles.
Wait, those ESP32 microcontrollers cost what, 15 or 20 bucks?
At most. You can buy them on Amazon. And what they achieve with these inexpensive components is the creation of a 12-slot distributed IR mesh.
IR being infrared.
Right. These standard devices utilize their built-in 940-nanometer infrared blasters to create a real-time 3D spatial intelligence system right there on the battlefield.
And the real innovation here isn't just the IR, it's what they're actively choosing not to use.
Absolutely. There are no cameras involved.
None.
None. There is no reliance on external infrastructure like GPS, satellites, or cell towers. And crucially, there are no SLAM algorithms.
SLAM being simultaneous localization and mapping. That is the standard software that almost all modern augmented reality headsets and autonomous drones use to guess where they are in a room by
Right.
constantly analyzing video pixels, right? So
Right.
why avoid it?
Because analyzing pixels is computationally heavy, and it introduces lag. SLAM relies on visual features, so if the lighting changes or smoke fills a room, SLAM fails.
Right. It gets confused.
Exactly. The ADP system relies on pure invisible infrared reflection triangulation. The 12 modes fire IR light and just measure the return time.
Like a bat using echolocation, but with light.
Yes. And they synchronize perfectly without needing an external atomic clock because they all pulse to that phase envelope 369 millisecond baseline we discussed earlier.
So for the operator kicking in a door, instead of relying on a fragile camera system that can be blinded by a flashlight, you have a network of nodes firing in Visible light perfectly synced to the millisecond, creating a flawless 3D map based strictly on the physics of light bouncing off walls.
It provides zero latency building clearance. It allows operators to detect threat heat signatures purely through the IR variance. I mean, the system generates a sub-meter accurate point cloud every 100 milliseconds.
That's insane. And how does this connect back to the dimensional security we talked about, the S10 coin?
Because the physical space and the mathematical network are bound together, imagine a hostile surveillance drone flies into that 3D IR space.
Okay.
That drone does not possess a valid S10 coin coordinate derived from the local 369 millisecond baseline.
So the system recognizes the dimensional mismatch.
Right. It's not that the drone has an invalid password, it's that the drone's data emissions do not align with the mathematical reality of that specific mesh.
Oh, I see.
To the network, it is an anomaly in the geometry, and it is instantly flagged as hostile.
It doesn't belong in the physics of the local network, so it becomes a target.
Yeah.
Which brings us to how the operator actually visualizes all of this. We've built the math, we've deployed the hardware, now we have to pull it all together into the tactical AR HUD.
The wireframe overlay we pictured at the beginning?
Exactly.
The documentation details a deep integration with Enduro Lattice AR goggles. Now, if you've ever used a VR or AR headset, you know they suffer from HUD drift.
All right, HUD drift. If you turn your head too fast, the virtual waypoint marker floating over a doorway will kind of slide off into the wall for a fraction of a second before the software catches up and snaps it back.
Yeah, and that lag occurs because the SLAM tracking algorithms take milliseconds to process the visual change. ADP solves this drift entirely by bypassing SLAM.
No.
They bind the S10 dimensional coordinate directly to the device's internal physical gyroscope.
Oh, wow. So there is no estimation or image processing involved at all.
None. The calculation is purely deterministic based on the physical movement of the gyro. The virtual data layer and the physical space finally speak the exact same mathematical language. No lag, no drift.
And the way these operators network together in the field is fascinating.
Yeah.
The Wi-Fi signals bouncing between the headsets aren't just sending data packets back and forth. They literally are the realized 3D space.
It's physical networking.
Yeah. You put 3 operators on the ground, and their radios form a lancelet delta formation. The signal measures distance by time of flight and angle by the phase of the wave.
And then they connect upward to a microsatellite in orbit. Those 3 ground operators, plus the 1 orbital node, create a massive tetrahedron.
A 3D volume of controlled space.
Exactly.
Yeah.
Everything inside that invisible geometry is deemed sovereign territory, strictly governed by ADP logic.
And within that sovereign territory, the intelligence gathering is absolute. This is where it gets really interesting for anyone worried about data privacy, not just military applications. They use something called the coin journey system, which acts like a passport.
A very aggressive passport.
Yeah, aggressive is the right word. When payloads leave this secure network and travel out into the open web, all personally identifiable information, every Facebook tracker, every Google Analytics tag is violently stripped away.
The guarantee is absolute privacy. Zero personal data survives the egress through the gate assembly. Only that 60 S10 coin exits, acting as an obfuscated, mathematically complex passport.
And when it comes back,
When it returns, it reports where it has been. You aren't tracking the human user. The coin is simply reporting its own mathematical journey.
think about what that would mean for consumer tech. A local mesh that makes your web traffic mathematically invisible to advertisers. And the UI they use to display this is intense.
The Geiger counter visualization?
Yes. Every time a tracking script is killed at the edge of the network, it registers as a click. The OLED wireframe interface literally shows the trackers being eradicated in real time as these coins return.
It provides a visceral, immediate representation of the security at work. But the ultimate realization of all this technology is what the inventor calls the spherical shield.
Right. As these coins accumulate and report back their journeys, they map points on a radiosphere. And once you gather enough of these multidimensional coins, they form an AI impenetrable Faraday cage.
A cage of math.
It is. It's a shield made entirely of infinite depth mathematics wrapping around the operators.
This is the dawn of S10L, the superposition 10 language. They are essentially inserting a brand new computing stack layer right between the physical operating system and the applications.
With its own instructions, right?
Yeah, it features a 9-instruction set designed purely for dimensional logic. Instructions like s10.mint, s10.root, s10.navigate. It fundamentally replaces how a computing device understands space, time, and security.
Okay, let's bring all this telemetry back to the command center and sum up this STREP. We have explored a platform that is actively rendering traditional flat space cybersecurity obsolete.
Completely obsolete.
It takes memory-heavy, vulnerable, probabilistic guessing and replaces it with deterministic, constant-time, multidimensional arithmetic. And it achieves this using cheap consumer hardware and infrared mesh networking, completely ignoring traditional servers and standard infrastructure.
It marks a profound shift. We are moving from relying on the physical walls of hardware to relying on the absolute, unbendable laws of mathematics itself.
So as we shut down the AR overlay, the wireframes fade out, and we return to reality, what is the final lingering implication of this that we haven't touched on yet?
Well, we've spent this entire time talking about ADP as a tool for defense and sovereign security, but consider the flip side. If an architecture like this becomes the global standard, if true mathematical invisibility and infinite depth encryption become accessible to anyone with a $20 dongle and a smartphone, how do governments or law enforcement agencies even function?
Oh, wow.
How do you police a network where the authorities literally lack the dimensional geometry to even perceive the existence of bad actors, let alone track them? If mathematical absolute invisibility becomes the standard, the concept of digital governance might simply cease to exist.
That is a terrifying and fascinating thought. If the police are trapped in 2D flatland, they can't arrest someone moving through the sixth dimension. You've been listening to a deep dive into the source material on the Apex Domain Protocol. Thank you for joining us as we unpack this tactical SI trap. Keep your overlays sharp, and we'll see you in the next deep dive.